All right, guys. I'm hoping this is working. Zoom has changed some of the settings. Um, this is chapter 10, Thermal Physics, Temperature Scales, the introduction to Physics 102. As I mentioned in the introduction session and discussion, I'm going to be using my own slides for these lectures. And I will have a separate video with problem-solving techniques and examples that are going to be similar to the ones in the assignments and assessments. The idea with this class or this lecture is to go over some of the basics, some of the parameters and terms that you are going to be learning and reading in your textbook and on the slides. So this is the Serway textbook that you can find online. Chapter 10, it has the temperature scales, it has the ideal gas law, and some of the kinetic theory of gases. Now, I will be covering this more with problems on the next video, okay? And the same with chapter 11, energy in thermal processes. Mainly today, we are going to be introducing scales, expansion, heat, specific heat, and conduction, convection, and radiation. Okay, so in terms of heat and temperature scales, many of you have discussed this either in high school or in chemistry. But when we are measuring temperature, we have different scales. We use Celsius, Fahrenheit here in the US, and Kelvin, mostly in science applications. For example, in astronomy, we use kelvins to determine the temperature of stars, of the inner core of stars, and of course of other celestial bodies. Celsius is what we use normally in daily life. And here in the US, we are accustomed to use Fahrenheit. Now, that is in terms of a temperature scale, which is not the same as heat. Heat is basically energy transfer that flows from a warm body to a cold body. Okay? That's why it's defined as the energy transfer between objects. Okay? So if you have object A and object B, if object A is warmer than object B, heat will transfer from A to B. Okay? That brings to the zero law of thermodynamics. We are going to be studying the first and the second law later, but the zero law states that if object A is in equilibrium, thermal equilibrium with object B, and object C is in thermal equilibrium with object B, then object A is in thermal equilibrium with object C. Okay, and what is thermal equilibrium? When they reach the same temperature. That is going to be an application that you're going to investigate in a lab when you do the calorimetry lab, and when in a lecture when we discuss problems of thermal equilibrium, basically by introducing a warm body or combining, having a mixture of a warm and cooler or a cold body, right? Basically, we do that to determine specific heats, specific heat capacities. Um, Now, when we have scales, as I mentioned, we have Celsius, Fahrenheit, and of course we have the Kelvin scale. Now, as a reference, the boiling point of water is 100 in Celsius and the freezing point is 0. So Celsius scale is very useful and very easy to use because you go from 0 to 100 and then you have a thermometer, and you have 100 divisions. So that's normally the reason why Celsius scale is the most commonly used scale around the world. Here in the US, however, we use the Fahrenheit scale, where you should know 32 Fahrenheit is basically 0 Celsius, and 212 Fahrenheit is 100 Celsius. So the first problems on the assignment are basically transformation between the scales. There is a linear relationship between these two, which is given here, right? The temperature in Fahrenheit is 9/5. The temperature, the relationship between Fahrenheit and Celsius, right? 9/5 times the temperature in Celsius plus 32 Fahrenheit. So 0 Celsius is 32 Fahrenheit. Now, if I want to convert 100 Celsius and get that to 112, then you can easily just go in the calculator, right? And then you do 9/5 times 100 plus 32, and that's 212. So that's why 212 Fahrenheit is equivalent to 100 Celsius. There's a linear relationship. It's very simple. If you rearrange this equation, you can get the temperature in Celsius 5/9, temperature in Fahrenheit minus 32. Be careful because there are parentheses here. Okay, so for example, if I want to go from 212 to Celsius, right, 100 Celsius, you will do 212 minus 32 first, then you multiply by 5 divided by 9, and then you get basically the 100 Celsius there. All right, so that is basically how this works. All right, from Fahrenheit, from Celsius to Fahrenheit, from Fahrenheit to Celsius. All right. Now, when we talk about temperature, if, especially for a gas like air, we have to remember this ideal law of gases that we are going to be learning or discussing later on in the course, where pressure is proportional to a temperature, right? PV equals to nRT. More temperature, more pressure. So at the zero pressure, we get the absolute zero. And the absolute zero, right, when the pressure is zero, is basically negative 233.15 Celsius. That is the 0 Kelvin, absolute zero, the temperature where all molecular motion stops, right? Because the definition of temperature is more complex than the definition of heat. We have temperature scales, but temperature itself is a measurement of the average kinetic energy of particles, right? Everything is made of atoms, and those atoms can create or can make molecules, right? And they are moving, right? They are vibrating, they are resonating, they are, we have atomic motion, right, inside an object. So the more motion, the more temperature. The less motion, the less temperature. That's basically how it works. So the temperature, microscopically speaking, is the average kinetic energy of particles. So when those particles stop moving, which is something kind of abstract because we have never been able to reach that in a lab, but theoretically speaking, when the pressure is zero, when the average kinetic energy of particle is zero, then that's when we reach the absolute zero, okay, which is 0 kelvins or negative 273 Celsius. All right, which is why or how we define the Kelvin scale, right? The Kelvin scale here is equal to the Celsius scale plus 273, pretty much, which is why 0 kelvins will be negative 273.15 Celsius. All right. Now, for very high temperatures, for example, the temperature of the core of the sun, which is about 10 million kelvins, is about 10 million Celsius. For very, very large temperatures, this relationship makes makes these two about the same. Not for Fahrenheit, but for Celsius and Kelvins, we end up talking about the same value. All right. Um, that's just how it is, right? This makes sense more for sort of like daily life sort of temperatures, right? Like, for example, if we're talking about the average temperature on summer, which is about 30 Celsius, 30 Celsius plus 273.15, that's about 303.15 kelvins, right? On winter, the average temperature may be what? 0, negative 5 Celsius, so negative 5 plus 273.15, then that's 268.15, right? So that makes sense, right? However, we're talking about the millions of Celsius or Kelvins, then this is kind of negligible. Here is a nice relationship there, right? We have the boiling point of water in Fahrenheit, Celsius, and Kelvin, the freezing point for carbon dioxide, for nitrogen, and then the absolute zero in 3 different temperature scales. All right. Now, in the next video, I'm going to solve some problems so you can see how easy it is to go from one scale to the other, right? At the end of the day, we are mostly going to be using Celsius and Kelvins for the problems of heat, thermodynamics, and even later on when we talk about gases and stuff. Now, when we talk about thermal physics and change on temperature, we have to talk about thermal expansion. You probably have heard about dilation or the dilation coefficient of materials, meaning that depending on the type of material, they will expand during a hot day of summer, right? Engineers take that into account when building railroads, right? During a hot day of summer and then during a cold day of winter, there is a change on length due to a coefficient of linear expansion, right? This is the change on the length is equal to the coefficient times the initial length times the change on temperature. So the larger the change of temperature, the more will be the change of the length. Now, this alpha, which is the coefficient, is normally not very big. That's why it's very negligible. There has to be a significant change on the temperature to actually see, maybe in the order of millimeters, a change on length. And it also depends on the material, right? The lead and aluminum, they have a higher coefficient of linear expansion. It also depends on the initial length, of course, but it mostly depends on alpha and delta T. Okay? And keep in mind that alpha is in units of Celsius to a -1. All right? Or Kelvin to a -1, depending on the change of temperature. If you are placing your change on temperatures in Kelvins or Celsius, at the end of the day, it doesn't matter because of the conversion itself, and you will see that in the examples. You can use either of these. The coefficients are the same anyway, right? The units just change. So this is used in bimetallic strips where you have two metals with two different coefficients. Therefore, they have different expansion rates. So you can have an expansion like this. You can have a bimetallic strip that when it shrinks more when it's cool, for example, B shrinks more when it's cool. Here, B expands more when heated. That's why it goes like this, or like this when it's cooled. Okay, so that is something that we can study and we take into account when we build materials in physics because of these different coefficients of linear expansion. Now, does the length or is the length the only parameter that changes? No, we also have the area and the volume, right? The volume of a solid will change, the area of a flat substance will change. And the only difference is that the coefficient of area and volume are basically twice and 3 times respectively, right? So this beta here is 3 times alpha. And for the area is 2 times alpha. So it's the same equation, just twice here, and here will be 3 times. Okay. So there are some typical coefficients of volume here for other substances like water, oil, right? Liquids that can expand, that have volume, and that can have volumetric expansion. Keep in mind how greater the coefficients are compared to the linear ones, right? These are in order of 10 to a -3. So it's easier to actually investigate the expansion, right? Or the volumetric expansion or shrinking of a substance due to a change, to a significant change on temperature, right? So, for example, water expands when it's heated. But there is a nice property of water. You see how the density of water peaks around 4 Celsius and then it starts decreasing again? So it also expands when cooling between 4 and 0 Celsius. That's because the density is increasing. This is why ice floats on top of water, right? It has less density. Ice has less density than water, than liquid water. That's why ice can float. This also explains why ice is only on the surface, and then you can actually go fishing on a frozen lake because there's water at the bottom, right? You can have a layer of ice on top and liquid water at the bottom because of this nice property of water between 0 and 4 Celsius, which again, you probably have discussed this on chemistry, right? The famous triple point of water. So that's with temperature scales. You will get more of this when I do the problems, all right, in the next video. Keep in mind that the main equations so far are the linear, volumetric, and area expansions, and of course the temperature scales. But there are more equations and more definitions once we get into heat, mechanical work, specific heat capacity, and such, right? There are nice experiments to show that work, right, and heat are basically related. Heat is basically another form of energy, and we can use that to create mechanical work. And there is even this Joule experiment where you can use electrical energy to heat up water. So basically, a direct relationship between joules and what we use in thermal physics, which is the unit of calorie. Heat is another form of energy measured in calories. And you should know that because that's basically what you guys, or some of you guys, do in the gym. You are burning calories by performing work, right? So you get exhausted, you are sweating, you are doing work, you are basically performing a task, you are releasing energy in the form of heat. So we have this device to show that. But we also have the definition of a calorie, which a calorie is defined as 4.18 joules, right? It's defined as the amount of heat needed to raise the temperature of 1 kilogram of water 1 Celsius. So if you want to reach the temperature of water by 1 Celsius, 1 kilogram of water by 1 Celsius, that's basically the calorie. Or in some places called the kilocalorie. Why the kilocalorie? Because we're talking about kilograms, right? Which basically gives you your definition of heat. Heat is defined as the amount of mass times the specific heat capacity times the change on temperature, measured in calories or joules. Depending on what you're using, you can directly measure this in joules. It depends what you are using for the specific heat capacity. Okay? The specific heat capacity, or start with the heat capacity, is the amount of heat by the change in temperature. Q divided by delta T. And now again, this change on temperature is normally measured in kelvins. It can also be measured in Celsius. But at the end of the day, when you do the difference, you are canceling the factors, right? The conversion factors. Regardless, you have here joules over kelvins or joules over Celsius. That's the capital C. But we also have the specific heat capacity, which is the amount of energy needed to raise the temperature of water by 1 Celsius, or by a substance by 1 Celsius. And that's why we have different specific heat capacities depending on the substance. Water has a very large specific heat capacity, meaning that you need a lot of energy to change the temperature of water by 1 Celsius. In joules per kilogram per Kelvin, or joules per kilogram per Celsius, the specific heat capacity of water is 4,186. Very high. If you compare it with other substances, for example, silver, gold, lead, which are very conductive, right, of heat, they have very small specific heat capacity. So in the calorimeter experiment, or when we do problems, you're going to realize that while substances like silver, aluminum, lead, they have a rapid change in their temperature, not the same happens for water, which is why water is defined as a perfect coolant, for engines, for example, right? You can have them in your car and it will not expand, it will not heat up very easily because of its high specific heat capacity, which is why it takes a while for water in the ocean to rise during summer, right? If you live up north, you know or you realize, right, you have encountered that the temperature of the ocean takes a while to reach values where you can actually enter and swim. Why? Because even though it can be very hot, water having a very high specific heat capacity takes a while to change its temperature, right? There are benefits for this, of course, that we can actually use in different applications, right? So these are some of the equations that we're going to be using in problems, and this is a table you can use as a reference. Let me just show you what you have in the book. So in the book you have the same, right? The zero law of thermodynamics. You have a few definitions which are the same as I've been going over. You have the Kelvin scale. You have here a few examples of how we determine some of those values that I explain, the pressure versus temperature graph that I show you, how we define the absolute zero, the unusual behavior of water due to its density, its variable density. And then in the book, they do go over the ideal gas law and the kinetic theory of gases. I'm going to go over that in the next lecture. But just so you know, the ideal gas law is what you have learned in chemistry, which is the relation between pressure, volume, and temperature. Okay? And you have the equation of state. PV equals to nRT, where n are the number of moles, R is the constant of gases, and T is the temperature in kelvins. Pressure is measured in atmosphere, or pascals, sorry, volumes in meter cube. All right. So just so you know, an ideal gas is a collection of atoms or molecules that move randomly and exert no long-range forces on each other. And also, I must add, where the collision among them are elastic. So there is no change or decrease of energy. There is no loss of energy. All of the collisions are ideal. So there is conservation of both energy and momentum. Okay? Yeah, so I will be going over this on the next slide. These more equations where we'll find the energy of gases, the density of a gas, and the root mean square speed of a particle in a gas. Okay, so you're gonna see more of that in the problems, right? Let's continue with this. Let's go and let's finish with this conduction, convection, and radiation. There are a couple of problems I posted in the assignment, but basically you have three ways where heat can be, or how heat is transferred. Conduction is probably the most common one, where you have different temperatures between a rod or a bar with a given length, and heat flows through the physical material from the hot spot to the cold spot. How does it do? It's proportional to the cross-sectional area, proportional to the constant that depends on the substance or the material. Is also constant to the temperature change, but is inverse proportional to the length of the rod. So here is the equation. The heat as a function of time, so Q over T, which is the rate of change of heat, is the constant K, the thermal conductivity, times the area, times the change of temperature, divided by the length of the rod. All right? So that's basically how we find heat conduction by using thermal conductivity. But you also have convection. By the way, here you have some thermal conductivity coefficients here, right? The more conductive, the higher the thermal conductivity. So silver obviously is going to have the highest, right? And you have glass, water, concrete, with the least amount of thermal conductivities. Again, we use those properties when building materials, for example, for a house, insulating materials and such. We take this into account to know what type of materials we need to create a perfect insulating place, depending by for summer or winter, inside a building or a house. Convection is the flow due to raising of warm air and basically the creation of convection cycles, right? A good example will be a hot day of summer where you have warm air rising and then going down like this, creating a cycle, right? This is normally applied when there is a fire, right? When there's a fire, what do? You have to crawl. Why? Because the warm air is going up while the cooler air is going down. This is also used when cooking, right? When you have a pot and you are cooking, the heating device is at the bottom and is heating the food. It's warming up, going up, and then whatever is up is going down, creating a cycle. So what is cool up there is gonna go down, it's gonna heat up, and it's gonna create this constant convection cycle, right? And then in terms of radiation, right, that's basically how we get heat from the sun. Without the need of a medium, it is transferred from the sun to the earth via electromagnetic waves, right? You can have different type of electromagnetic waves that we're going to study as well in this course. You have infrared, visible light, ultraviolet, right? Which, unlike conduction, it doesn't need a medium. It can go through vacuum, okay? The amount of energy radiated by an object is proportional to the surface area, which in the case of the sun will be 4 pi r squared, the total area of a circle. The force temperature of the body, and what we know as the emissivity. It's a constant that goes between 0 and 1. And it's also proportional to the Stefan-Boltzmann law, or the Stefan-Boltzmann equation, constant here, which is given by this. All right. So this is similar to what we know in astronomy as the luminosity equation, which is proportional to the area and the fourth power of the temperature. The Stefan-Boltzmann equation there and the emissivity there, right? So that's basically what you should know for the introduction of this course. Again, chapter 10 is mostly about temperature scales, heat, specific capacity, and thermal conductivity. Now, let's show you what you will be expecting on the first assignment. Oh, yeah, physics 102. So, for chapter 10, you have 10 questions. The first questions are about changing the temperature using the equation. So I will go over some similar questions on the next video. Question 1, question 2. Then here is a review of finding number of moles. That's mass over molecular mass or mass over atomic mass. So you need a periodic table for this. Here you have a little bit about gases. And here you have a little bit about the kinetic theory of gases. And here you have a little bit more about temperature, some of the ideal gas law, all right? So I will be going over similar problems in the next video, so make sure you watch it, all right? The main thing about this is that in some of these you have to change the units, right? Liters to meter cube, moles is fine, pascals is fine. See how the temperature has to be in kelvins, and the energy in joules. So keep in mind that I'll be going over these questions on the next video, temperature and ideal gas, right? In the next assignment is where we're gonna have more of the heat and calorimetry sort of problems. Yeah, so specific heat is here, specific heat, and then you have here thermal equilibrium and such, all right? I will also go over phase changes that will be posted on the next video or the next module. So this video will be posted here, and the next video will also be posted here, here. I'll be posting another video here with problems on thermal physics, another video here with thermodynamics, all right? Remember that you can access the assignments here for chapter 10 and here for chapter 11. So after the first or second week, you should be able to start doing assignments 10 and 11. Remember to complete the discussions and to also send me any questions you may have about the class, about the problems, about the due dates, okay? Without further ado, I will wish you guys to have a very nice day and see you guys on the next video. Bye bye.